So shall we start now? Can you see the screen? Can you see the screen, whatever I shared?
Yes, ma'am.
Okay. So yesterday we have seen the definition of Floquet system. Floquet system is nothing but the system u at t plus 1 is equal to a of t ut is called a Floquet system if this a of t is periodic with minimum period p. What is mean by a of t is periodic with minimum period p? A of t plus p is equal to a of t. Then we say that it is a periodic with period p. For example, this scalar type of a of t we have seen minus 1 raised to t, and you can see here a of t is equal to minus 1 raised to t is periodic with period 2, right? Let me that is a of t plus p is equal to a of t, and here it is with period 2 means that is a of t plus 2 is nothing but again minus 1 raised to t plus 2. So it is nothing but say a of t. Is it okay? This is Floquet system. And then we have proved the lemma. If C is a non-singular matrix and P is a positive integer, then there exists a non-singular matrix B such that B raised to P is equal to C. So now we will see discrete Floquet system. Discrete Floquet's theorem. So what this theorem states that theorem, this is 4.13, discrete Floquet's theorem. Floquet's theorem.
मॅम स्क्रीन दिसत नाहीये.
मी लिहिते ते दिसत नाही का?
नाही मॅम.
Share the screen.
दिसतीये ना मॅम.
दिसते मॅम.
दिसतं ना?
हो मॅम
दिसतंय
दिसते.
हा
मॅम. ओके,
हा,
सो
आता
ज्याला
दिसते.
दिसत नाही त्यांना प्रॉब्लेम. ओके.
दिसते मॅम.
Okay. So I have started theorem 4.13, discrete Floquet's theorem. Can you see this in red color?
Yes ma'am. Yes ma'am.
Okay. So what this theorem states that if phi t is a fundamental matrix, if phi t is a fundamental matrix for the Floquet system, Floquet system 4.16 means it is u at t plus 1 is equal to a of t u of t, where a of t is periodic. Then phi at t plus p is also a fundamental matrix. Is also a fundamental matrix, and phi at t plus p is equal to phi t times p, where c is nothing but a at p minus 1, a at p minus 2, and so on, a at 0. Furthermore, there is a non-singular matrix. There is a non-singular matrix function p of t, capital P of t, and a non-singular matrix B, non-singular matrix B, such that phi t is equal to P of t b raised to t, where P of t is periodic with period p, where P of t is periodic with period p. Small p, this is small p. So this is the statement of Floquet's theorem. What this says that if phi t is a fundamental matrix for the Floquet system, u at t plus 1 is equal to a of t ut. It is a Floquet system means a of t is with period p, some minimum period p. So if phi t is a fundamental matrix, we have to show that phi of t plus p is also a fundamental matrix, and phi at t plus p can be written as phi t times c, where c is nothing but a at p minus 1, a at product of matrices a at p minus 1, a at p minus 2 into so on a at 0. Furthermore, also we have to prove that there exists a non-singular matrix function p of t and a non-singular matrix b, such that phi t can be written as p of t times b raised to t, where p of t is again periodic with period p. Whether statement is clear? So what is given? Phi t is a fundamental matrix. What is mean by a fundamental matrix? It satisfies this equation, this system, and it is non-singular. Determinant is non-zero for all integers t. Then we say that it is a fundamental matrix, right? So assume that phi t is a fundamental matrix. Or instead of assume, we will say given that phi t is a fundamental matrix of the Floquet system. What is the Floquet system? U at t plus 1 is equal to a of t ut. So this implies phi at t plus 1 is equal to a of t phi of t and determinant of phi t is non-zero for all integers. Okay, this is by definition of fundamental matrix. We can give number to this Floquet system. Also, system 1 is Floquet system implies A at t plus p is equal to A at t. Okay, that is A of t is periodic with period p. Now we want to show that phi at t plus p is a fundamental matrix. So when we say that phi at t plus p is a fundamental matrix, if it satisfies and its determinant is also non-zero. So let psi t is equal to phi at t plus p. Then if phi t is non-singular, then phi at t plus p is also non-singular. Then psi t is also non-singular means for all integers t, for all integers t. And what is psi at t plus 1? Psi at t plus 1 will be phi at t plus p plus 1, but phi at t plus p plus 1 will be what? A at t plus p, phi at t plus p, right? Phi at t plus 1 is A of t into phi t. So phi at t plus p plus 1 will be, t will be replaced by t plus p here. So A at t plus p, phi at t plus p. But what is A at t plus p? It is A of t. I will give number 2 to this. Which is nothing but A at t, phi at t plus p. So this I can write as A at t into psi t. We have used here from 2. Is that right? So what it shows that, so this implies psi t, which is equal to phi at t plus p, is a solution of the system, of the Floquet system is also, phi t is also there, psi t is also a solution of the Floquet system given by 1. So what this, it is non-singular, psi t is non-singular and psi t is also solution, means this implies psi t is a fundamental. This implies psi t is equal to phi at t plus p is a fundamental matrix for the system 1. So first part we have proved it is a fundamental matrix. Now what we have to prove? We want to show that phi at t plus p is equal to phi t times c, where c is nothing but this. So we have already proved a theorem. If phi t is a fundamental matrix, it can be written as another fundamental matrix. It can be written as phi t times some c, where c is some non-singular matrix. So also by theorem 4.10, there exists a non-singular matrix C such that phi at t plus p is equal to phi t times c. We already yesterday we have proved this, right? Phi t plus p is equal to phi t times c for all integers t. So with t is equal to 0, what will be this? Phi t, phi p,
Phi of P.
phi p will be phi at 0 into c.
C.
So this implies c is nothing but c can be written as phi inverse of 0 into phi p, right? Pre-multiplying by matrix phi inverse of 0 on both sides. What we get? C is equal to phi inverse of 0 into phi at p. Now, what is phi at t? Now, phi at t plus 1 is nothing but a of t into phi of t. Since we have phi at t plus 1 is equal to a of t phi t, what can be phi at t plus p then? Phi at t plus p, phi at t plus p will be a at t is it? What should be phi at t plus p? Or instead of that, we will write
to 5.
wait. Instead of that, what we want to show here, c is equal to, it should satisfy phi at t plus p is equal to phi t times c. It came from that theorem itself, where c is phi inverse of 0 into phi at p. Now, what will be therefore from I can write here. So c is equal to phi inverse of 0. What will be phi p? Instead of phi at t plus p, what will be phi p here? If p is equal to t plus 1, what will be this?
A of t minus 1.
No, t minus 1 nahi hai na, no. T plus 1 is nothing but p. So what will be t? A at p minus 1, phi at p minus 1. Can I write like this? Phi inverse of 0 as it is. Let me write on next line. Phi inverse of 0 as it is. What is phi p? Phi p will be a at p minus 1, phi at p minus 1. Can I write like this?
Yes, ma'am.
Because here t plus 1, instead of t plus 1, we are taking t. So whenever it is t, it will be p minus 1, 1 reduced. Now, phi inverse of 0, a at p minus 1. Now what is phi at p minus 1? A at p minus 2, phi at p minus 2.
Yes, ma'am.
Yes. Now again, if I go on iterating like this, now what is phi at p minus 2? A at p minus 3, phi at p minus 3, right?
Yes, ma'am.
So if I go on iterating like this, what I will get last in last, and so on. If I go on doing like this, phi inverse of 0, a at p minus 1, a at p minus 2, and so on, what will be last? P minus p, a at p, phi at p, sorry, a at 0, p minus p, and phi at 0.
Yes,
Is
ma'am.
it right? Yes. So now phi inverse of 0 and phi at 0. I can write this as a at p minus 1, a at p minus 2, and so on. A at 0, phi inverse of 0, phi at 0. So this will be identity matrix. So I will just get p minus 1, a at p minus 2, and so on, a at 0. So that is my required C. That only we want to prove, right? C is equal to a at p minus 1, a at p minus 2, a at 0. Is it okay?
Yes, ma'am.
Now we want to prove there is a non-singular matrix function P of t and a non-singular matrix B such that phi t can be written as P of t times B raised to t, where P of t is periodic with period t. So now, so we have already proved by previous lemma. Lemma whether we have given number, lemma 4.1. Yesterday we have proved lemma, this lemma. Yes, lemma 4.1. Okay. So from this lemma, what we will have? There is a non-singular matrix. There is a, by previous lemma 4.1, there exists a non-singular matrix B, so that B raised to P is equal to C. Yesterday we have proved this, right?
Yes, ma'am.
Because C is non-singular, so there exists integer P such that B raised to P is equal to C. For there exists a non-singular matrix B such that B raised to P is equal to C for some integer P. So let P of T. Now I want to show there exists a matrix function, so I will define that matrix function. P of T is equal to phi T times B raised to T. So let P of T is nothing but phi T times B raised to minus T. So this will be also non-singular. B is non-singular, phi T is non-singular, so product is also non-singular. Note that P of T is non-singular for all integers T. And what is P at T plus P? What is P at T plus P? It is phi at T plus P B raised to minus T plus P. This I can write as, what is phi at T plus P? Phi at T plus P can be written as phi T times C. And this I can write as minus T B raised to minus P. So let me erase this. B raised to, I can write this like this. But what is C times B raised to P? B raised to minus P. From what number I can give here? Third I have here. Third. We are having B raised to P is equal to C. So what is C times B raised to minus P?
1.
Identity. Instead of 1, it is identity. So phi t times B raised to minus T, identity I will write. So, but phi t times B raised to minus T is nothing but my P at T. You can write here since or using 3. So P at T plus P is equal to P at T. So what this means? This implies P at T is periodic with period. What is the period? Minimum period?
P.
Small p. Okay. And so we have considered this means that is what is my phi t, or I will give number 4 to this. Also from 4 what is phi t? Phi t can be written as P of t, capital P of t, B raised to t, where P of t is periodic with period p. So this proves the theorem. Is it okay?
Yes, ma'am.
Now we define Folkwatt's multiplier. Next definition. Folkwatt's multipliers. Folkwatt multipliers. So the eigenvalues mu of the matrix C is equal to A at P minus 1, A at P minus 2, A at 0. Just now we have shown that C can be written as A at P minus 1, A at P minus 2, A at 0. So the eigenvalues of that matrix are called as Folkwatt multipliers. Okay. If phi t is a fundamental matrix of the Folkwatt system, then there exists a non-singular matrix C satisfying this A at P minus 1, A at P minus 2, A at 0. And if we find eigenvalues of that matrix, that eigenvalues are called as Folkwatt's multipliers. The eigenvalues mu of the matrix are called as Folkwatt multipliers. For example, what is Folkwatt system we have seen? For example, consider the Folkwatt system. What is simple example we have seen? U at t plus 1 is equal to minus 1 raised to t a at not a at t, u at t. We have seen this is a, we know that this is a Floquet system with period 2, right? Consider the Floquet system where a of t is nothing but minus 1 raised to t is periodic with period 2. So what will be my C? So therefore C will be nothing but, what is A at P minus 1? P is 2. So A at 2 minus 1 means
1.
And A at 2 minus 2. So that is nothing but A at 1, A at 0. What is A at 1?
0.
A at 0. A at 1 is
Minus 1.
minus 1 raised to 1. Minus 1 raised to 0 means 1.
1.
Now minus 1 ka minus 1. Yes, minus 1 raised to 1 is minus 1. And this is 1. I will write here. So we are getting here minus 1. So since this is a scalar, means only single matrix, so eigenvalue is the same, which is scalar, we can write here with is a periodic scalar matrix. Therefore C is equal to this is a scalar matrix. Or which is a scalar matrix. Which is a scalar. Scalar matrix means 1 by 1 matrix with eigenvalue mu is also minus 1. Therefore the with the Floquet multiplier is 1 minus 1. Okay, so for this system Floquet multiplier is minus 1. Is that okay?
Yes, ma'am.
Another example we will have. Consider or find the Floquet multipliers of the Floquet system. Floquet system where t plus 1, it is 2 by 2 matrix now, 0, 1, minus 1 raised to t, 0, y at t. So what is A of t here? What is A of t? It is 2 by 2 matrix, 0, 1, minus 1 raised to t and 0. So what is the period for this? Which is periodic. What is the period of this matrix? Which is periodic with period 2. Because what is A at t plus 2? What is A at t plus 2? 0,
0 power
1,
1 minus 1 raised to t plus
minus 1 raised to t plus 2 and
1, 2.
So,
0.
but minus 1 raised to t plus 2 is same as minus 1 raised to t, which is nothing but minus 1 raised to t and 0, which is equal to a of t, right? Therefore, it is periodic with period 2. Now to find, therefore, C, what will be my C? Therefore, C is equal to what then? If it is period, with period 2, at P minus 1 means 2 minus 1,
A
2 minus
A of
2.
1, A of
That
0.
is A at 1, A at 0. What is A at 1?
0, 1, minus 1, 0.
Minus 1, 0. A at 0 is 0, 1,
0,
1,
1, 1, 0.
0. What is the product? 0, 1, 1, then 0, 0, then
0.
minus 0,
Minus 1.
and minus
Minus
1.
1.
So what are the eigenvalues of this matrix?
Minus 1.
Because it is triangular matrix, eigenvalues of the matrix C are 1 and minus 1, right? So consequently, what are the Floquet multipliers? Mu1 is equal to 1 and mu2 is equal to minus 1. So there will be two Floquet multipliers. Is it?
Yes, ma'am.
So it depends on what is my A of t. If A of t is a scalar, only one Floquet multiplier. If A of t is 2 by 2 matrix, then two Floquet multipliers will be there. If A of t is 3 by 3 matrix, then it will have 3 Floquet multipliers and so on. Now we let me we will have this theorem also. Next theorem. So today we can complete this syllabus. Some half an hour extra we will require, but we can complete it. Assume that mu is a Floquet multiplier for the Floquet system u at t plus 1 is equal to a of t u of t, then there exists or there is a non-trivial solution yt of the equation of the equation u at t plus 1 is equal to a of t ut, such that y at t plus p is equal to mu times y at t. What is mu? For all integers t, where mu is the Floquet multiplier, right? Assume that mu is a Floquet multiplier for the Floquet system. Then we have to show that there is a non-trivial solution yt for the same equation which satisfies yt plus p is equal to mu times yt. So assume that, so here given that mu is a Floquet multiplier. Floquet multiplier means it is eigenvalue for the matrix C, where C is nothing but A at P minus 1, A at P minus 2, A at 0. Floquet multiplier for the equation for the system 1. Then, so this implies mu is the eigenvalue of the matrix C where C is equal to A at P minus 1, A at P minus 2 up to A at 0. Now let what is given this, we want to show there exists a non-trivial solution yt. So we will take y as a eigenvector of C. Let y be an eigenvector of C of matrix C corresponding to eigenvalue mu, and phi t be a fundamental matrix of equation 1. Then we define yt is equal to phi t times y. What is y? Small y. Y is an eigenvector corresponding to eigenvalue mu, and phi t is a fundamental matrix. So we are defining yt as phi t times y, where y is the eigenvector. So yt is an what can I say? Then yt is a non-trivial solution of equation 1, and by Floquet's theorem, there exists phi at t plus p. Phi at t plus p is equal to phi t times c. Just now we have proved this theorem. So we have, what is y at t plus p? It is phi at t plus p into y. But what is phi at t plus p? It is phi t times c y. But c is what? C is a y is a eigenvector of matrix C. Okay, so what can I can write phi t is equal to mu times y. We can give here, since y is an eigenvector of matrix C. So this corresponding to eigenvalue mu. So this implies A lambda is equal to what we write usually. AU is equal to lambda u, na, if u is an eigenvector. So here Cy is equal to mu times y. This is eigenvalue. This is eigenvector. Is that right? So phi t times mu y. So what can I write? What is phi t y? It is mu is a scalar, phi t y. But phi t y is nothing but my yt. Mu times yt for all integers t. Is it right? That only we want to prove.
Yes.
We want to prove that yt plus p is equal to mu times yt. So we have shown that there is a non-trivial solution yt which satisfies this. Now theorem 4.15. What this theorem says that let phi t is equal to p of t b raised to t, as in Fouquet's theorem. Then yt is a solution of the Fouquet system u at t plus 1 is equal to a of t ut if and only if z of t is equal to p inverse of t into yt is a solution of the autonomous system z at t plus 1 is equal to b times zt. What this theorem says that let phi t is equal to p of t b raised to t. Just now we have in Fouquet's theorem we have proved that phi t can be written as p of t b raised to t. So if phi t is equal to p of t b raised to t, then yt is a solution of the Fouquet system u at t plus 1 is equal to a at t ut if and only if this zt is a solution of the autonomous system z at t plus 1 is equal to b times zt that we want to show. So it is if and only if statement. So assume that yt is a solution of system 1, we will say Fouquet system 1. Then if it is a solution of system 1, then column vector will be solution of scalar equation. Then there is a column vector w so that yt is equal to phi t w. Just now we have proved this. And what is my phi t? Phi t is nothing but p at t b raised to t w. Now we define zt is equal to p inverse of t y at t. But what is P inverse of T, it is B raised to T W P inverse of T YT is nothing but B raised to T W, right? From here, YT is P of T B raised to T W. So P inverse of T YT, P inverse of T YT म्हणजे इकडच्या साईडला, so it will be B raised to T W. Is it right?
Yes, ma'am.
So now, so it follows that what will be, so this implies ZT is a solution of Z at T plus 1 is equal to B times ZT. It satisfies that equation. And converse follows by reversing the steps. Next theorem is stability theorem for Floquet system. Theorem 4.16. Stability theorem. If mod mu is strictly less than 1 for all Floquet multipliers, then every solution YT of equation ZT plus 1 is equal to A of TUT satisfies limit T tends to infinity Y of T is equal to 0. So as we seen in stability criteria for autonomous systems, linear equations, if all eigenvalues of the matrix are strictly less than 1, then every solution tends to 0 as T tends to infinity. The same will apply for Floquet. If all Floquet multipliers are strictly less than 1, then every solution will tends to 0 as T tends to infinity. Same case, only instead of eigenvalues here Floquet multipliers will be there for Floquet system. Now if mod of mu is strictly less than or not strictly, if it is less than or equal to 1 for all Floquet multipliers, and every multiplier mu with mod mu is equal to 1 is simple. Then there exists constant D so that mod of YT is less than or equal to D times mod of Y0. This also we have proved for autonomous system. If Floquet multipliers are less than equal to 1 and for which mod mu is equal to 1, if it is simple, then there exists a constant d, so that mod of yt is less than or equal to d times y at 0. And third, if some multiplier mu satisfies mod of mu is strictly greater than 1. If it is strictly greater than 1, then there exists a solution which tends to infinity as t tends to infinity. Then there is a solution yt of equation u at t plus 1 is equal to a of t ut, so that mod of yt tends to infinity as t tends to infinity. Okay, so we'll skip the proof of this theorem. We will just require the statement of the theorem for solving examples. So we can have example. It is analogous result for whatever we have proved in stability third one, fourth, this one only. This is stability of nonlinear systems, stability theory. Two theorems we have proved. What's the algorithm? The spectral radius, you can see, if spectral radius is greater than equal to 1, some solution ut of equation u at t plus 1 is equal to a times ut does not go to origin, means it tends to infinity as t tends to infinity. So this is equivalent to C. Is it right?
Yes, ma'am.
And I think previous you can see here this. Let A be n by n matrix and spectral radius is less than 1. Spectral radius is less than 1 means mod of all eigenvalues are strictly less than 1. If it is strictly less than 1, then every solution ut of this equation satisfies limit t tends to infinity ut is equal to 0. Is it? Is it the same? And if spectral radius is strictly less than delta, I think one next theorem, then asymptotically stable. 2 points were there. Theorem. You can check that there were A and B options. Spectral radius is less than or equal to 1, and for the eigenvalues for which multiplicity is 1. 1 means they are all simple. Then there exists a constant D which satisfies that condition. Okay, you can check in this. We will have example now. Find the Floquet multipliers. For the Floquet system, where t plus 1 is equal to 0, 2 plus minus 1 raised to t upon 2, 2 minus 1 raised to t upon 2, and 0. Via t. And use them to determine the stability of the system. So first we have to check whether it is a Floquet system. It is a Floquet system. Here, what is A of t? A of t 0, 2 plus minus 1 raised to t, 2 minus 1 raised to t upon 2, and 0. That is my 2 by 2 matrix. So what is the period? Whether it is periodic? Since A at t plus 2, what is A at t plus 2? 0, 2 plus minus 1 raised to t plus 2, 2 minus 1 raised to t plus 2 divided by 2, 0, which is same as A of t. Is it right?
Yes, ma'am.
Because minus 1 raised to t is same as minus 1 raised to t plus 2, minimum period. Similarly, minus 1 raised to t plus 4, t plus 6, and so on. But minimum period is 2. So since this, therefore, A of t is periodic with minimum period 2. Therefore, there exists a matrix C such that A at 2 minus 2, A at 2 minus 1. 2 minus 1 and 2 minus 2. Same. So A at 1, A at
0.
A at 0. So what is A at 0? A at 1 and A at 0. A at 1 will be
0.
0, 1 by 2, check it, 3 by 2, 0. And t is equal to 0, what you will get? 0, 3 by 2,
0.
1 by 2, and 0 again. Is the same. If you substitute 1 here, 2 minus 1 is 1 by 2. Here 2 plus 1 is 3 by 2, right? So A at 1 is 0, 1 by 2, 3 by 2, 0. And if I substitute 0 here, minus 1 raised to 0 is 1. So here it will be 3 by 2, and here it will be 1 by 2.
1 by 2.
Right? So A at 1 and A at 0. So if we multiply it, what we will get? 0, 1 by 2, 1 by 2 is 1 by 4, 0, 0, 3 by 2, 0, 3 by 2, 3 by 2, 9 by 4 plus 0. Is it right? Matrix multiplication. Therefore, eigenvalues of the matrix C are 1 by 4 and 9 by 4, right? 1 by 4. So that is, or this implies Folkwaite multipliers are mu1 is equal to 1 by 4 and mu2 is equal to 9 by 4. So whether all Folkwaite multipliers whose modulus is less than 1, what can we say? Only for mod mu1 is here, mod mu1 is strictly less than 1, but mod mu2 is strictly greater than 1, right? 4 to the 8.
Yes.
So it is strictly greater than 1. So by this theorem, what can I say? If some multiplier mu satisfies mod mu is strictly greater than 1, then there is a solution yt which tends to infinity as t tends to infinity. So it is not stable. Okay. So from above theorem, theorem कितने नंबर कितने 4.16 C, there is a theorem 4.16C, there exists some solution, there is some solution mod of yt which tends to infinity as t tends to infinity. However, notice that eigenvalues of a of t are plus or minus under root 3 by 2 for every t. So the fact that eigenvalues have absolute value less than 1 for every t is no guarantee of stability for non-autonomous system. Stability for so here eigenvalues of a of t are plus or minus under root 3 by 2 whose absolute value is strictly less than 1, but still we cannot guarantee that it is a stable because of Folkwaite multipliers. One Folkwaite multiplier is strictly less than 1 and another one is strictly greater than 1. Is it okay?
Yes, ma'am.
So this completes our syllabus. For 4.5 already we have seen stability of nonlinear systems. The Cloquet system 4.4 we have kept as last topic because it has been added like earlier in earlier syllabus it was not there. Now from this year only this new syllabus has been started. So in that Cloquet system and that has been added. So this completes our syllabus. If anything is there, we will have, we can meet Monday now for seminars then. So from Monday onwards, will you give seminars? Hello students.
Yes, ma'am.
So from Monday onwards, we will have seminars. So Monday, Bhojne Punam, will you be ready? Whether Bhojne Punam is there? Bhojne Punam, are you there? So inform Bhojne Punam to give seminar on Monday and then sequence wise you can give seminars, okay? So we can stop here.